In mathematics and computer science, currying is the technique of translating the evaluation of a function that takes multiple arguments into evaluating a sequence of functions, each with a single argument. It was introduced by Gottlob Frege, developed by Moses Schönfinkel, and further developed by Haskell Curry. Uncurrying is the dual transformation to currying, and can be seen as a form of defunctionalization. It takes a function f that returns another function g as a result, and yields a new function f that takes a number of additional parameters and applies them to the function returned by function f. The process can be iterated. Motivation. There are analytical techniques that can only be applied to functions with a single argument. Practical functions frequently take more arguments than this. Frege showed that it was sufficient to provide solutions for the single argument case, as it was possible to transform a function with multiple arguments into a chain of single argument functions instead. This transformation is the process now known as currying. Currying is similar to the process of calculating a function of multiple variables for some given values on paper. For example, given the function to evaluate, first replace with since the result is a function of this new function can be defined as next, replace the argument with producing on paper, using classical notation. This is usually done all in one step. However, each argument can be replaced sequentially as well. Each replacement results in a function taking exactly one argument. This produces a chain of functions as in lambda calculus, and multi-argument functions are usually represented in curried form. Some programming languages almost always use curried functions to achieve multiple arguments. Notable examples are ML and Haskell, where in both cases all functions have exactly one argument. If we let f be a function, then the function h, whereas a curried version of here is a function that maps an argument y to result z, in particular, is a curried equivalent of the example above. Note that currying, while similar, is not the same operation as partial function application. Definition. Given a function of type currying, it makes a function, that is, takes an argument of type and returns a function of type. Uncurrying is the reverse transformation, and is most easily understood in terms of its right adjoint, apply. The operator is often considered right associative, so the curried function type is often written as. Conversely, function application is considered to be left associative, so that is equivalent to. Curried functions may be used in any language that supports closures. However, uncurried functions are generally preferred for efficiency reasons, since the overhead of partial application and closure creation can then be avoided for most function calls. Mathematical view. In theoretical computer science, currying provides a way to study functions with multiple arguments in very simple theoretical models such as the lambda calculus, in which functions only take a single argument. In a set theoretic paradigm, currying is the natural correspondence between the set of functions from 2 and the set of functions from to the set of functions from 2. In category theory, currying can be found in the universal property of an exponential object, which gives rise to the following adjunction in Cartesian closed categories. There is a natural isomorphism between the morphisms from a binary product and the morphisms to an exponential object. In other words, currying is the statement that products in homo-adjoint functors, that is, there is a natural transformation. This is a key property of being a Cartesian closed category, and more generally, a closed monoidal category. The latter, though more rarely discussed, is interesting, as it is the suitable setting for quantum computation, whereas the former is sufficient for classical logic. The difference is that the Cartesian product can be interpreted simply as a pair of items, whereas the tensor product, used to define a monoidal category, is suitable for describing entangled quantum states. Under the Curry-Howard correspondence, the existence of currying and uncurrying is equivalent to the logical theorem, as tuples corresponds to conjunction in logic, and function type corresponds to implication. Curry is a continuous function in the Scott topology. Naming. The name currying, coined by Christopher Strachey in 1967, is a reference to logician Haskell Curry. The alternative name of Schönfinkelization has been proposed as a reference to Moses Schönfinkel. In the mathematical context, the principle can be traced back to work in 1893 by Frege. Contrast with partial function application. Currying and partial function application are often conflated. One of the significant differences between the two is that a call to a partially applied function returns the result right away, not another function down the currying chain. This distinction can be illustrated clearly for functions whose error t is greater than 2. Given a function of type currying produces. That is, while an evaluation of the first function might be represented as, evaluation of the curried function would be represented as, applying each argument in turn to a single argument function returned by the previous invocation. Note that after calling, we are left with a function that takes a single argument and returns another function, not a function that takes two arguments. In contrast, partial function application refers to the process of fixing a number of arguments to a function, producing another function of smaller rarity. Given the definition of above, we might fix the first argument, producing a function of type. Evaluation of this function might be represented as. Note that the result of partial function application in this case is a function that takes two arguments. Intuitively, partial function application says, if you fix the first arguments of the function, you get a function of the remaining arguments. For example, if function div stands for the division operation x, y, then div with the parameter x fixed at 1 is another function. The same as the function inv that returns the multiplicative inverse of its argument, defined by inv equals 1, y. The practical motivation for partial application is that very often the functions obtained by supplying some but not all of the arguments to a function are useful. For example, many languages have a function or operator similar to +_1. Partial application makes it easy to define these functions. For example, by creating a function that represents the addition operator with one bound as its first argument.